Welcome to our talk on record serialization. In the next 30 minutes, we want to share a happy tale with you, and that is how records, a new feature in the JDK, can be leveraged in serialization. To answer this question, we break it down into 3 parts. We first look at the concept of serialization and then focus on Java's serialization framework. In the second part, we look at records, why they were added to the JDK and what they bring to the platform. And then in the third part, we bring those 2 parts together to explore what advantages records have in the context of serialization. When I say we, I mean Chris and myself. My name is Boes. I work on the OpenJDK as part of the Java platform group at Oracle. I joined in 2019 and have been working on record serialization for the last few months.
Hi, my name is Chris Hegarty. I'm a consulting member of technical staff in the Java platform group at Oracle. I've been working on Java platforms since I joined Sun Microsystems way back in the year 2000. Uli and I work in the same group, but clearly these days, as most people are, we are working from our own homes.
Before we dive in, please have a quick look at the safe harbor statement. While it's unlikely that records will change before general availability of JDK 16 in March, it's still possible. Okay, let's start with the first part. So you see a little diagram here, and there's a JVM on the left-hand side with an example foo object. And then on the right-hand side, you have a file system, which could as well be a JVM that is connected over the network. Now, serializing really means to extract an object state and translating it to a persistent format. And deserializing, on the other hand, means to reconstruct an object with equivalent state from that very format. When I say format in this presentation, I'll mostly talk about the serialized form, and commonly that's a serial byte stream. So serialization in general is a very powerful concept, and many frameworks have implemented it. One of them is Java Serialization. So in Java Serialization, in order to be able to serialize an object, its class has to implement serializable. That's a marker interface with no behavior or state. And once that's done, the class is serializable. That kind of seems too easy, and in fact, the flaws of Java serialization are well known and many. Brian Gutz gives a good overview of the problem space in the article that is linked below here. In the context of this talk, I want to highlight 3 points that are especially relevant. The first one is it's an extra linguistic feature. It seems like a library feature because you can implement an interface, but under the hood it uses privileged mechanisms like reflection, it ignores accessibility, and it bypasses constructors. So there's quite a lot of dark magic that is hidden to the developer. The second point is that the compiler won't help you. So for example, this foo class, let's say it had a field of a type that was not serializable, you wouldn't get a compiler warning, but the error would occur at runtime. The third point is the magic methods. So yes, you can let the framework do everything for you, or you can implement one of the many special methods and fields. The problem here is that they are hard to discover because they don't belong to a public type, and they're also quite easy to get wrong. So for example, you can use the wrong access modifier, or let's say the wrong list of parameters. So with Java Serialization, you can either depend on the framework, which means you're relying on a lot of opaque mechanisms, or you can implement it yourself, which is very powerful, but also very error-prone. To conflate this, the core of the problem is really that Java Serialization is not designed as part of the object model. So there's no explicit formalized way of extracting the object state and reconstructing an object that is properly baked into the object model. So much so that it's actually possible to create impossible objects. And that's a term coined by Joshua Bloch in Effective Java. Let us explore this with an example. So here we have an example normal class, statue. It has 3 private final fields, a string name, an int height, and a location. Location is a second helper class with 2 private final fields, string city and a string country. Both classes implement serializable, and both classes have a constructor that does invariance checking. We don't want the objects to be null or the height to be equal to or less than 0. The boilerplate is omitted here, and we don't have setters because the state should be final. So now with this, we create a statue object, a very specific one. The Statue of Liberty has a height of 46 meters and a location in New York. So now the choice of example might seem peculiar to you, but there are two things serialization and the Statue of Liberty have in common. So the Statue of Liberty was constructed in France, the parts were, and interestingly, the statue was actually put together and erected in Paris. It was fully intact there for a while before it was disassembled again and then created for its voyage to the US in 1885. So for example, here you can see the face that had just arrived on Liberty Island. On Liberty Island then, it was reassembled again to the proper statue. So that is very much like analog serialization. The second similarity is that the statue has also been object of magical activity. In 1983, David Copperfield made it disappear on live television. It was very traumatic, and both the audience on the ground and on TV were kind of taken aback when the curtain fell and the statue was gone. And while this is not serialization per se, I think the awe of the audience when the statue is gone is something that developers who have worked with Java serialization can relate to. Because here, object state can change in unexpected ways and impossible objects can be created. So let's go back to the example to show this in detail. We have our statue object and we want to serialize it with the default mechanism. That would be to call object output stream write object, and we write the serialized form to a file in this case. The framework really handles the rest, but this is already one example of an extra-linguistic mechanism. Because behind the curtain, the state of the fields is scraped, and you remember they were all private fields, and then written to the serialized form. The framework uses reflection to do this, in particular set accessible true. So it circumvents access control with a backdoor technique here. Okay, we now have a serialized form at hand. And this is just a bit of a simplified version for demonstration purposes. But what you can see really is that it's like a container holding the object data. So we have the type statue, and then we have the fields, each with a name, type, and value. And if the value is an object, then you can see there we have a second object container nested in there. So that's relatively straightforward. Deserializing is the more interesting part. So let's look at that. Now we want to deserialize the statue from that serialized form. The default way here is to call object input stream read object, and then cast the object that is returned. Again, the framework handles everything else for you. What is important here now is that the object creation during deserialization happens from top down. So we start reading the stream, and as soon as the type is known, an object is created. Now this is important. The object is created by invoking the null arg constructor of the first non-serializable superclass. In this case, that's object. So it's really not the statue constructor that we so carefully constructed with the invariance checking, but it's a completely different constructor that is called. This also means that the fields are set to their default values. You can see that here, null or 0. And so there is a window of time where the statue object is in an erroneous state. We continue reading the stream, and the values are populated in the object, as you can see. And once we get to the nested object, the same thing happens. The object constructor is called. The fields are set to default values. They're then populated with the values from the stream. And only once the objects are created, the objects are actually linked up. So that's only at the end of the deserializing process. So now location is no longer null, but it's pointing to the location object. The read object method returns, and we have reconstituted the statue object. So all good, you might say, but you might also say, we really rely on the data in the serialized form here to be the correct data. What if that's not the case? So, for example, let's say we work with a malicious stream. As you can see here now, the serialized form holds data that would violate the class invariance. We have a height of -1 and a location of null. That's not possible for a statue. And oh yeah, just to notice, so this object would not have been created in our JVM because there's no constructor to do that, but you could assume that it comes from another JVM or from some untrusted source. So the same thing happens again. We read the stream for deserialization. The object is called with the null arg constructor of the first non-serializable superclass. Fields are set to their default values. And once we're done and read object returns, you can see that we now have a completely flawed statue object at hand. The read object method returned and is oblivious to the fact that the object is impossible. The invariance checks in the statue constructor are never applied. So kind of the statue is there, but it's not there. And I think David Copperfield would be at awe. To recap the problems of Java serialization. During serializing, the framework is able to extract the state of private fields. So it circumvents access control via reflection. And then during deserializing, the class constructor is never called, it's bypassed, and instead the superclass constructor is called. So those two aspects are what it means when I say Java serialization was not designed as part of the object model. Okay, so we know what's wrong. Now let's move on to section 2 to see what records bring to the table. And for this, I hand over to Chris, who will do what I call an in-IDE sales pitch.
Thanks, Julia. So what are record classes? A record class is a plain aggregate of data. There's less ceremony in the declaration of a record class than that of a normal class. And we like to say that records are all about the data, the whole data, and nothing but the data. A record is a nominal tuple, so it has a name. It's a transparent carrier of data, so it makes all of its data available to its clients. There's a new syntax in the Java language for declaring a record class. And a record class tightly couples its API to its internal representation. The declaration of a record class is significantly more concise than that of a normal class. So what does all this mean? Let's take a look at an example. So we've seen the location class earlier, and the location class is an aggregate of a city and a country. You might want to use a location class in a hash set or a key in a hash map. So really we need to provide equals hashcode implementations as well as a toString implementation, so we have a reasonable experience when we're debugging. So this code I've written earlier, I'm just going to paste it in here. It does the obvious thing. Two locations are considered equal if their cities are equal and their country is equal. And then the hash code is computed from the city and country. And additionally, the toString implementation contains the city and the country as well. So this code is a little bit tedious to write. It's not very exciting code, and it's a place where it's easy to make mistakes. And really, it would be better if we didn't have to write this code in the first place, even though it's important that these implementations exist. Fundamentally, the location class is about two things. It's an aggregate of a city and a country, and that's exactly what records give us. So let's convert and rewrite this location class as a record class. So there's a new keyword, record, for declaring records. Immediately following the record keyword, we have the name of the record class, which is location in our case. And then in parentheses, we have the record header, which contains the components of the record, so the state of the record. And in our case, we have two pieces of state, the city and the country. And that's it, we're done. So the main program here, let's just run it and see if it outputs what we expect. So it creates a new location for New York in the US, and then just prints out that location. So here we can see the string representation of the record being printed out. I'm using early access build of JDK 16. Records are a final feature in JDK 16. In JDK 15 and JDK 14, they were previewed. So if you're running with JDK 14 or 15, you need to run with the enabled preview flag. Okay, so it's a plain aggregate of data. We have seen our location aggregates a city and a country. There's less ceremony, so we declared our location class in a single line of code. It's all about the data. We've seen that the city and the country are upfront with the name of the class in the declaration. It's a nominal tuple, so our record class is a location class, but equally its state components, the city and the country, have also got names. It's a transparent carrier of data. We'll look at that in just a moment. And it's a new kind of class, so we use the record keyword in its declaration. And the syntax and the declaration is far more concise than that of the normal class equivalent, which we've just seen. There's a little bit else going on here. So the compiler generates for us the public accessor methods for a record class. It will generate a canonical constructor, and it will generate the hash code equals and toString implementations as well. And record classes are also always final. So if we take a look at the decompiled output of the location class, so here we're going to use the Java P decompiler to output the location class file. So we can see that the class is final. It extends Java lang record. Every record class extends Java lang record. The compiler has generated a private final field for each of the components, city and country, as well as a public accessor for the values of the components. Compilers also generated the hash code equals and toString implementation. And lastly, the compiler has generated us a single constructor. This is the canonical constructor. The canonical constructor has the same formal argument list as that of the arguments or the components in the record header. So there's two strings. The first is the city and the second is the country. Okay, so we have seen accessors, canonical constructor, toString, equals, and finality. We say that a record class is a transparent carrier of data because it makes its record components available. It's not possible to have a record class that has fields that are not part of the record components, either public or private. Additional fields can only be declared within the record header itself. And this allows us to tightly couple the API and internal representation. So the canonical constructor constructs the record with a number of components, and then the accessor makes the components available. Okay, so what if you don't like what the compiler generates for you? You can provide an explicit accessor for each of the components, or you can provide an explicit constructor. Records also have a compact version of that constructor. A record class is a restricted class, but equally it's still just a class, so it can have additional implementation methods, and it can also implement interfaces. Okay, let's work through a few of those. Let's say we want to provide an explicit accessor for the city method, and this accessor is going to always normalize the value of the city component. So it's going to return city in uppercase, for example. Okay, so let's update our test program to invoke the city accessor, and then we just run it. Okay, we can see New York being printed out in uppercase. What if we wanted to ensure that we couldn't create a location instance that had a null value for either the city or the country? So we can provide an explicit constructor, and we're going to give that constructor the same arguments as that of the record header. This is a canonical constructor, and we'll do the assignments to the internal fields. Morally, this is what the compiler generates for us, but we want to do some additional argument checking. So we'll use objects require non-null to ensure that both the city and the country are non-null. Okay, so this is a little bit of boilerplate still in this code. because we know the canonical constructor has the same formal parameter list as that of the record header. So the compact constructor allows us to elide that. And additionally, the field assignments can be elided. And this leaves just the main logic of what we want in our program, which is the null check on the city and the country. Let's just ensure that that works as expected. So here we expect a null pointer exception to come from the location constructor. And okay, great, we can see that here. Okay, so we've seen an explicit accessor that normalizes the city component. We've seen a canonical constructor that does some invariant checking, and we've seen the compact form. Now let's take a look at a implementation method. Let's say, for example, we want a method that reverses the city. Here we'll use string builder because it offers us the functionality without too much effort. And we will move to a new location. And we will invoke the reverse city method. Okay, let's run the program again. And we expect to see Atlanta printed out in reverse. Okay, great. You can see that. Record classes can also implement interfaces. So let's say we have an interface city, a single abstract method, also named city. We can have our location record implement that interface. Now here, there's no need to provide an explicit implementation of the city method because the compiler generates that accessor for us anyway. But of course, we could have something like comparable, in which case we'd need an implementation of the compare_to method. And as we will see in just a moment, we can also have record classes implement serializable. Okay, we can check these off now. Okay, so some key points about records. The design of records centers around modeling data as data. And by giving up some of the flexibility of regular classes, we get these nice semantics. And then the boilerplate just takes care of itself. The API is derived mechanically and completely from the state description. And the API includes protocols for construction through the canonical constructor and member access through the accessor methods. And then you get equality, hash code, and string representation for free. We expect future versions of records to support deconstructor patterns to allow for more powerful pattern matching. And now Ulia will take us through how Java Serialization has been able to take advantage of the strong semantics of records.
Okay, on to part 3. How can we leverage records in serialization? Now that you know more about records, let's go back to our example and work with record classes instead. You see here we now have a statue record class and a location record class. Both have the same fields. We call them components now. And both still do the same invariance checks in the constructor. The constructors both have this nice compact format that Chris showed you. To make these record classes serializable, we use the exact same mechanism, implements serializable. However, under the hood, the framework handles a record quite differently. The reason for that is that the concise design of records really allowed to rethink the serialization protocol. So for records, the protocol is based on 2 properties. The first one is the serialization of a record is based only on its state components. So the serialized form is based on the components and cannot be customized. The second part is the deserialization of a record uses only the canonical constructor. The canonical constructor is never bypassed and is the only constructor that is called during object creation. The simplicity of this protocol kind of naturally flows from the semantic constraints of records, and they really show how serialization is now a proper part of the object model for records. So back to our example, we instantiate a statue record and we write it to a file just as before. The serialization framework can now access the record components with the provided accesses, so there's no need for backdoor techniques here. And we get our serialized form. It's the same as before, and it's literally the exact same as for an ordinary object. This really allows for easy migration from normal classes to record classes. Before we look at the deserializing side, just a slide with the steps, because they differ from normal classes. The difference is that for normal classes, we construct the object graph from top down. For records, we do the same from bottom up. While reading the values from the stream, that means that we don't create an object first, but we first read the values and reconstruct them. So either reconstruct an object or hold primitives in memory. And then we match those values against the record components. That matching happens by name and value, and any values that don't match a record component are dropped. And then only as the last step, we call the canonical constructor with the values as arguments. So onto the example, and we're going to deserialize it now. We have the serialized form, and I'm going to speed it up here a little bit. The important bit you already know. The object is not created first. The values are read from the stream and reconstructed. So in this case, we have the string Statue of Liberty, and we have the int. And now we have this nested object. So again, we don't call the constructor of the location object first. Instead, we read the New York string, we read the second string, and at this point, we now have all the values that we need for the canonical constructor of location. We call it, and now we have this complete location object. This is now also the time where we have all the values that we need for the canonical constructor of the statue record class. So we call that, and now we have the complete statue object in our hands. As you can see, that there's no time that an invalid object is available, so this is definitely more secure than what we've seen before. However, what happens if we work with a malicious stream again? As you might remember, we have the invariance checks in the constructors, so it shouldn't be possible to create a record object that violates these. We're going to use the same malicious stream again. The height is -1, the location is null, and we start reading the serialized form, we hold the values in memory, and as you might already expect, yes, it's not possible to create a record this time around. What happens is that we have this null check in the constructor for the location object, and that catches that we pass null, so a null pointer exception is thrown. Great, it's not possible to create an impossible record. To finish, let's sum up how records make serialization better. 4 points. The first one, the design of records really naturally fits the demands of serialization. They are data-oriented classes, which are naturally suitable, but also because they have very restricted extensibility and final state, it's so much easier to handle them during the serialization process. So really, the semantic constraints that they have allow a tightening of the serialization protocol. The second point is that the serialized form is known and can be trusted. It's always the record state. There's no customization allowed. This is much easier to understand and also to maintain. The third point, you can always use the accessors to retrieve record state. You don't need to use magic techniques. This is more secure. And as a last point, object creation is only allowed through the canonical constructor. So with this in mind, we hope that you are just excited about records as we are, and you go and try them out. Thank you.